go. The easiest criterion is the so-called maximum stress criterion, which is very similar to the yield, the Tresca yield criterion, I think, in metals. You basically determine the stresses parallel to the fibers. So in this case, the subscript X denotes parallel to the fibers. And you compare it to the XT value here. So if the stress in a ply exceeds this value, obviously, then it has to fail. That seems reasonably obvious. And similarly, if the X, sigma X parallel to the fibers is compressive, instead of using this value, you would use that value. Experimentally, those are quite different, and that's important. In metals, the tensile yield and compressive yield for most alloys of aluminum, let's say, are reasonably close, within a few percent. Here, they can be off by more than 30%. Similarly, if you have loading in the Y direction, then Y direction being perpendicular to the fibers, then you would use the tensile or compressive strength perpendicular to the fibers. And again, if the applied stress exceeds the allowable strength of the material, then you have failure. And finally, you would have the shear. I put the absolute value because whether it's positive or negative, you just take its absolute value and compare it to the measured shear strength. And if it exceeds, then you are in trouble. Now, you can logically think that if I only have one single stress, let's say sigma X were the only one applied, this criterion makes perfect sense. And in fact, it works very well if you have only one single stress. But if you have a combined state of stress in a ply, then it's not at all obvious that it suffices to compare the stress parallel to the fiber to the corresponding strength. And if it doesn't fail, you say, no, okay, I have no failure. And then the sigma Y to its corresponding strength value and so on. That's where combining the stresses becomes important. If you think physically, suppose I have failure in the matrix because of tension in the matrix. If I have shear, that doesn't mean that the matrix cannot carry any shear now, because essentially I have these cracks in the matrix which are simply shearing, and yes, they are moving around as I apply the shear load, but that doesn't mean they cannot take some load. So obviously, a single failure according to this criterion does not mean I have correctly predicted failure if I have a multiple state of stress, multiple state of stress in that ply. The complete counterpart, instead of using stresses, using strains, is shown here. So basically, you compare strains to the corresponding strain allowables. Now, if you had a perfectly linear system, so there is no, the stress-strain curve is completely linear, then the two criteria would only differ by the Poisson's ratio effect between stress and strain. Please.
The stress that we're looking here is a combination of matrix and the fibers, or only fibers? Or?
It's the ply stress. That's a good question, whether the stress is the combination of matrix and fibers or just individual. It's the ply level stress, which means you have already translated fibers and matrix into a single ply with the stiffness matrix ABD matrix, and you are calculating the corresponding stresses and strains for the entire ply. It's not on the fiber level or on the matrix level alone. So there's a maximum strain criterion, or then it starts getting interesting. People are saying, instead of using the individual ones, I recognize that somehow they combine either destructively and they cause earlier failure, or constructively and they delay failure. So Steve Tsai, now retired, a very famous person, not only for the criteria that he came up with, took a theory by a gentleman called Hill, which was developed for metals, for anisotropic metals. There was a yield theory that he developed, and he said, I will take that theory and translate it over to composites, which was the first big mistake he made, not in terms of being wrong, but in terms of exposing himself to a lot of criticism. We'll talk about criticism a lot. In the sense, if you are the first one to do something, if you do it perfectly, then everybody uses what you did. If you do it very well, but there you leave room for criticism, then a lot of people will criticize, and we'll see the criticisms as we go. What he said is, if I try to take the limiting case of a composite becoming a metal, I want whatever expression I will derive for a failure criterion to, in the limiting case, give me the behavior of that metal. Now, physically, that has absolutely no reason why it should happen, because the mechanisms of failure in composites are different, and therefore there's no reason why. But it's a very nice way of trying to encapsulate both metal and composite behavior. So it turns out if you put them in this form, again, the sigma x, sigma y, tau xy are the applied stresses on your ply at the ply level, and x's and y's and s's are the corresponding tensile or compressive stresses depending on the sign of those applied stresses in the ply. So if this left-hand side is greater than 1, you have failure, because it means that at least enough of these numerators are greater than the denominators, and therefore the applied stresses are greater than the strengths. Then there was a generalization that Steve Tsai and Ed Wu did, which said, okay, this really doesn't recognize the fact that I can have different tension strength and compression strength in a composite, while, as I said, in metals, those tend to be close enough that you can use a single value. So let me now introduce the xt and xc, which are the individual tension and compression values, and the yt and yc for transverse, and the s value here. Now this criterion becomes this one. And in fact, there's a whole mathematical derivation that derives this and makes sure that this criterion, if you had an isotropic material, would give you the yield, the von Mises yield criterion. Again, arbitrarily was chosen by these gentlemen, Steve Tsai and Ed Wu, to do it so that there's a limiting case recovered by that criterion, and that was one of the main reasons there was a lot of criticism. Parenthesis, Ed Wu was unfortunately, he passed away, a brilliant guy that used to work for the US Air Force. And if you work for the US Air Force, unfortunately or fortunately, you also have to teach pilots, and pilots are not necessarily inclined in learning composites. So the story goes, and I have it from a sure source, that he would basically cut deals with the pilots to take him up on their F-16s and their F-14, hang on, F-14 is Navy, whatever the Air Force, F-18 maybe. They take him up and for a ride, and then he would help them a little bit on passing the courses. But he was a brilliant gentleman, and we'll come back to him if I remember as we go. I need to introduce another gentleman in a little bit. If I have pure tension, I can show that most criteria, and this is an example here, will give me about the same predictions. So this is my angle theta for a laminate that's 0 to theta 2 minus theta 2 symmetric. The reason this laminate is selected is because it has very peculiar failure behavior. And the gentleman working with me these days has actually created this, which shows the failure load on the y-axis as a function of the theta location, as predicted with 3 different criteria, Puck, the maximum stress we just saw, and the Hoffman criterion. And interestingly, in most cases, the predictions have nothing to do with what happens in reality. Even though the criteria seem to agree, in reality, the minus theta plies, no, the plus theta plies will develop a crack, a matrix crack first, which is a transverse failure. Then you get a delamination between the plus theta and the minus theta, which none of these criteria can predict, and then you get final failure. So this is to show that even though the criteria agree with each other reasonably well, they might not be close to what the actual specimens would do. And recognizing this problem, many people have tried to compare actual test data, shown here, with different criteria. And this is a gentleman called Edge from England, John Hart-Smith, which is a guy I need to introduce right now, and Puck, which is probably the best criterion we have today. And you will see that they differ quite significantly in some locations in the envelope. And in some cases, they are unconservative, as at the bottom left here. In others, they are quite conservative. John Hart-Smith, a brilliant gentleman from New Zealand, who used to work for Douglas Corporation, McDonnell Douglas, actually became a fellow. Fellow for these companies means that you are recognized as a worldwide authority in what you do, and he was very good at composites. In fact, he developed the best, for quite a while, for decades, the best methods for joint analysis of bonded joints and bolted joints, among other things. He's the kind of guy who over the phone could solve a problem. You would tell him, I have this kind of sandwich, and he would tell you, without you having enough time, based on the loads, what the thicknesses should be, for this to work. He's also responsible for the so-called 10% rule, and we'll talk about the 10% rule a lot in this course, so just in the back of your mind, keep that in mind, but that's John Hart-Smith. Then when Boeing bought McDonnell Douglas, he became a Boeing fellow, and he has now retired, living in New Zealand. He was the first one to openly, aggressively criticize this approach of coming up with failure criteria that look mathematically elegant, but capture very little of the physics. And I will show you what he thought in a little bit. And he attacked, sorry, going back, he mainly attacked Steve Tsai or Tsai and Roux for their criterion or the criteria of this type. That brings me to the other story I wanted to say, which is in a conference years ago in the early 90s, there was this big hotel in Lake Tahoe, and there were the people going for the conference who were interested in the conference and the papers being presented. Ed Wu was there. And the people who were going there because they wanted to go on vacation, had nothing to do with the conference. So for those people, there were all kinds of electronic games. And one of the games at the time, which was very popular, you had this big screen. We're talking 1991, so it was this huge screen, and you had a gun. You were like a Western cowboy, and you would be seeing the streets of a city, and a city of, you know, a saloon and a bar and everything, and you would be walking through, and different people would be attacking you, and you had to shoot them down, and of course not all of them were the bad guys. So Ed Wu was seen holding that, and every time he was shooting, he would say, Hart-Smith, Hart-Smith, Hart-Smith. He was pretending to be shooting Hart-Smith, but he was a very nice guy. Both of them are. So the stresses or strains in this criteria are parallel and perpendicular to the fibers in each ply. That's important if you're doing a failure prediction using this criteria, and you will be doing that for homework 1. You take the applied load, you translate it to strains. From those strains, you calculate the ply level strains, and then you relate those to stresses. Those are stresses in the original coordinate system of the laminate, and you have to rotate. All that is explained also in the textbook in case you are not familiar. But so if my original X and Y coordinate is like this, and these are my plies, I have some kind of loading. Let's say I have a bending moment being applied. This translates to strains through the thickness in this coordinate system. And those strains I can relate now to stresses for each ply in this coordinate system. But if, let's say, for this top ply, my fibers are at an angle to this coordinate system, I have to rotate the stresses I calculated in this coordinate system to the local coordinate system. We saw everything about stress transformation last time. Pretend this is perpendicular to that. So in the 1-2 coordinate system, and then you take those stresses and you put in these criteria. So if you take the laminate stresses, then you get useless results. They only predict failure of that specific ply in that specific failure mode. For example, if I'm saying this is my, not this one because it's difficult, if I'm saying sigma x exceeds xt, all I can say is that I have failure of the fibers in tension for that ply. Do I have final failure for the entire laminate? I don't know. That's all I can say. So it can be very conservative because it only predicts onset of failure, first ply failure. Hence the name first ply failure criteria. They cannot predict in principle final failure. What you have to do now is you have to say, okay, the load that was in the ply that failed has to somehow be carried by other plies. You make an assumption, logical assumption, how that's carried by the other ply, and you can go into post first ply failure criteria or progressive failure. And people have done that with mixed results. It doesn't work with a simple approach that says, for example, if the matrix fails, I set the transverse properties of the ply that failed to 0. That won't give you final failure in the end, except for some simple laminates. Everything we said is in plane, and unfortunately composite will fail out of plane because the matrix that connects the layers between them is very weak. And We need special criteria which have been, again, developed, but they require determination of the stresses out of plane, or they require fracture mechanics with energy release rate calculations. Given all this mess, in 1982, my professor, when I was a student, a master's student, Professor Lagasse, said or wrote, there are as many failure criteria as there are researchers in the field. I think the latest count is more than 70 failure criteria. And the consensus has yet to be reached. That was in 1982. Now, he also developed his own criterion, quite useful for out-of-plane failure. So if you are into this field, you'd better have your own criteria at some point. So 30 years later, in 2014, we are pretty much at the same situation. We have approaching 100 failure criteria, none of them working well enough. And in fact, scientists all over the world, or researchers, got together and they did the so-called worldwide failure exercises, and you can look into that into the internet. This is now at its third attempt. There was the first worldwide failure exercise, the second one. I think they're doing the third one now, and we still haven't found a good enough criterion. Zvi Hashin, I think now retired in Israel, a very famous also professor working on the topic, known for the Hashin criterion, said that he was asked about failure criteria and his opinion, and in fact his own criterion, and he said, my only work on this subject relates to failure criteria of unidirectional fiber composites, so it's not even with multiple orientations, not to laminates. I must say to you that I personally do not know how to predict the failure of a laminate, and furthermore that I do not believe that anybody does. So what are we doing here? And you actually have a homework for starting Monday. Well, we have to live with reality. I mentioned the gentleman, John Hart Smith, who is the main attacker of the Sai-Ru criteria. Look at this. This is actual publications, and if you are as famous and as smart, you can get away with this. The relevance of most composite failure criteria to conventional fiber polymer composites is claimed to have remained undetected. Basically, he's saying the composites fail in a completely different way than these criteria imply. Then the Sai-Hill failure criterion. Nothing in Hill's work addresses more than one mode of failure, and he should therefore be spared the ignominy, this is a New Zealander speaking, of association with the many abstract mathematical failure theories for composite materials. Yet, in the UK and Europe, Sai's misinterpretation of Hill's theory of anisotropic plasticity is referred to as the modified Hill theory. And it should now be evident that the innumerable abstract mathematical failure theories are beyond redemption as useful structural design tools. Yet everybody uses some version of them, recognizing that they are not accurate because there's no other way of doing it. It is clear then that the unstated simplifying assumptions of traditional composite failure theories are so contradictory to basic laws of physics that the theory should be discarded. That's why he came up with two failure criteria, which themselves don't work perfectly well, but they are physics-based, at least make an attempt. As a message to you, if I don't poke my eye out, as a message to you, the best criteria we have now that seem to work in many more cases than others is the PAC criterion and the LARC3. The LARC3 is much more complicated, but it's based on the PAC criterion. LARC3 means Langley Research Center. 3 is the third version. There's also a LARC4. In fact, I know the guy that developed this with some colleagues. My message also to you is keep that in the back of your mind, so if you talk to a purist and they start telling you this criterion is not good, you know where they're coming from, but you still have to generate a prediction today for your structure that's going to be flying tomorrow, and you need something to get started, to decide how many plies to put together, and then basically to decide what to test. So use whatever you like. I recommend any version of the maximum stress, maximum strain, or my personal favorite, which is the one that's been attacked the most, the Sai-Wu criterion. Those I have programmed into my computer, and those are the ones to check your results. But if you use a different one, that's fine. Any legitimate criterion, legitimate. Don't come up. If you come up with your own, better have a good explanation. If you convince me, I will accept it. If you don't, then you lose a lot of points. So let's switch now to the real course. This was all the review. So you're supposed to know all this stuff. Where's my glasses? So we'll start by, now we've done failure, sort of. We've done stiffness properties, classical laminar plate theory. Let's now start thinking about real structures and what we need to predict how real structures behave. Yes, I'm sure most of you know, but so I'm going a bit quickly. A typical airframe will consist of all kinds of members, each of which has a special purpose. There are beams, shown here, the longitudinal beams at on the floor. There are stringers on the skin. There are skins that are not shown so we can see through. Bulkheads, which are just glorified frames. There are fittings, and so on, each of which has a purpose, and each of which has to be analyzed, each of which has to be first designed. So let's take a real scenario here. This is real life now. To design a whole aircraft, you have to take it through all the possible maneuvers. It has to make turns at different radii, at different rates, accelerations. It has to do climbs and dives. It has to even crash and so on. You have taxi, crash, then the flight maneuvers, and then all these are static and fatigue versions, which ends up being a list of about 2,000. It's at least 1,000 if you do it right, about 2,000 maneuvers. So that means that 2,000 load cases. And let's say at each location in your aircraft, you have at least three different design concepts. For example, if you're doing skins, you can have the so-called stiffened skin with skin and stiffeners, or a sandwich, both of which we will cover in this course. Or you can have the so-called grid stiffened structure, where you have these tiny grid that actually stiffens your structure and gives you strength. Three alternatives. Now, for each of those, you may have three different ways to make it. For example, if it's skin on skin with stringers, you can co-cure, which means both of them go together, and then you go in the autoclave and cure, and out comes out the perfect structure. Or you can cure them separately and then use fasteners to hold them together, which is more like the black aluminum old method of doing things. Or you can use an adhesive. This color here is meant to be adhesive between the two. So I have three alternative designs, three different ways to make it, 2,000 maneuvers, 18,000 combinations, and that's a single layup to pick up one of the stacking sequences at one location in my structure. So if I'm trying to now optimize the layup to come up with the best layup among all these possibilities, each of those possibilities, the best way to do it is with genetic algorithms. We'll talk about genetic algorithms in the second course, in the next quarter, but I'm sure most of you have heard. What that allows you to do is to evaluate a lot of designs very quickly and find the best ones and use those to generate improved designs until you converge to something that satisfies all the requirements and is the lowest weight, let's say. But to do that, you would need to do a whole bunch of iterations, which ends up being about 15,000 different designs for one case. So all this means you have to do 270 million analyses for an aircraft. If you're trying to do 270 million analysis, you need to do more than 500 per minute if you're working 24 hours a day, 365 days a year, to finish them all in 1 year. So if you are going to do this with finite elements, which is the most accurate method, you will never finish. That's why this course, or courses like this, can be useful. You are not going to get the methods that are the best methods in all cases, but they will be reasonably accurate to give you a quick design which allows you, for example, to do optimization and do these 270 million analyses much faster than using finite elements. In fact, Airbus back in 2009 were saying that within an aerodynamics context, but it's exactly the same story. You can either test everything or you can analyze everything. And they said that running computer models at different attitudes is costly, whereas in a wind tunnel, the model can simply be rotated and the impact measured. So no matter what people tell you, we don't have the computer power and the speed to actually do all these cases accurately enough, and we need to compromise and back off. So the structural design process has a basic objective, which says I'm given a series of requirements, and I will need to come up with a structure that meets those requirements and has certain desirable attributes. And what all this means is, for example, I'm told that you have to fill in, the structure has to fit into this space, because if it goes outside this boundary, then it interferes with something else. And I have some applied loads and applied displacements potentially and hard points that I can use to hold my structure. And after you spend some time doing those millions of iterations, you come up with the best design, which has these lightning holes with reinforcements around them and locations where you can actually apply the loads and react the loads and so on. So that process, going from the blue blurb here to real structure, is partly what this whole course is about. And you have to do that, satisfying, first of all, the basic design requirements, which are the 3 Fs, fit, form, and function. It has to fit there without interference, it has to perform the function, and will have to have the proper shape to actually perform that function. It has to meet the applied loads, and then there are all the other desirable attributes. Should be corrosion resistant, the natural frequencies should be reasonable because we don't want any kind of resonance happening. Thermal expansion coefficient for space applications is a big deal. You want to keep that as low as possible, or at least compatible with between the different parts of your structure so you don't develop thermal stresses. You need to provide attachments for other structure, paths for other structure, and so on. This is the nightmare of any structural engineer. You have this perfectly good design, optimized, and then here comes the systems person and electronics person and says, by the way, there's lines that have to go through hydraulic lines or electrical lines. I need holes there. And you don't have an option, because they always win the argument. And then you have to redesign. We'll talk about some of this more. So the desirable attributes, and we are wrapping it up. Minimum weight, minimum cost, and then you can split this. Recurring, which means every time you make something, you minimize the cost. Non-recurring, which is the associated with the investment that goes once. Basically, the molds that you make to make a part, minimizing that cost, because that can be one of the drivers depending on how you operate as a company. Assembly cost, and so on. Low maintenance, replaceability across assemblies. If you, until 10 years ago, you took a part from one aircraft, tried to fit it in the exact same location in the nominally the same aircraft, it wouldn't fit. There would either be a gap or it would be slightly bigger because of tolerances, which we couldn't control well enough with standard touch labor-based processes. Now that everything is becoming more and more automated, we can actually drive those tolerances down, and you can replace across assemblies. Specific natural frequency placement, for example, a helicopter fuselage, if its natural frequency is close to the driving frequency from the blades, not only is it a very unhappy ride for the people in because they vibrate like crazy, it's not a very long ride either because eventually you have failure. Zero coefficient of thermal expansion for space applications, and so on, and you can combine these. We will continue this discussion on Monday.